So I'm Fernando, and well, this is the topic of my talk. So when you put a molecule close to a surface, there are a lot of different processes that can arise. For instance, when you excite with light an electron in this simple chemical picture, the HOMO is excited to the LUMO orbital. And then, if you are close to a metal surface, this excited electron can be recombined to the hole in the HOMO and emit light, but also this electron can be transferred to the metal. And in this case, you are going to be deactivated without the emission of the photons. And also there are a lot of different processes that you can observe in this kind of systems, because you can have hot electrons that are transferred from the surface to the empty orbitals of the molecules, and you can induce chemical reactivity. And well, as you can see, there are a lot of different recent works in these topics, because ultrafast processes, as Nicolas said, has a lot of different implications, for instance, in optoelectronics. So we develop a computational strategy which is dividing the use of density functional theory standard, let's say quantum chemistry calculations, to obtain the structure of the systems, and then wave packet propagation to follow the electron dynamics. For the electronic structure, we use DFT, just VASP code, the plane wave basis, pseudopotentials, and we use this OPTPB functional, which takes into account some weak interactions such as van der Waals interactions. Okay, so just for the structure, we can observe some interesting features in this interface. As Manuel Yañez mentioned the other day, we can observe how this chemical bond, this is the acrylane, and this should be planar, and it is planar in the gas phase. But when the molecule is absorbed on a copper surface, we see some sp3 character of this carbon. And this is because there is some density which is transferred from the surface to the molecule. And this charge transfer is going to be populating this empty orbital of the molecule, and is going to distort and to change the hybridization of the system. We can also, using DFT, we can see the region of the molecule where we are going to put this electron density, just the density of the molecule and the surface minus the density of the different parts, and we observe in green the region where this electron density is accumulated, and this is very similar to the LUMO orbital in the gas phase. So again, with this chemical simple picture, we can have a lot of information. We can study the projective density of a state, which is kind of the molecular orbitals, but in the solid state. And if we compare the projective density of a state, so the contribution of the molecular states when the molecule is far and when the molecule is close, we observe that these two states, these two occupied states, the p and the lone pair, are going to hybridize with the metal surface, and we are going to have the localized states. And also this p star orbital is going to mix, and is going to have the energy of the Fermi level, because it's going to mix with the metal states. So with this, we can characterize this kind of interaction, a donation from the lone pair and the p orbital to the metal, and a back donation to the pi star. So in some way, we can see that this interaction induces kind of a HOMO-LUMO excitation. So the effect of the surface is going to induce a chemical a rearrangement of the electron density. And well, this change in the electron density can be observed in the bond distances and in the harmonic frequencies. And also, if you carry out molecular dynamics, you see that the fragments that you obtain when the molecule is in the gas phase or when the molecule is on the surface are totally different. For instance, this is the Lewis structure of the molecule in the gas phase, and here we have a double bond. And that is why, when we are in the gas phase, we don't see this CH2. This is a double bond, so it is not possible. I mean, it is possible, of course it was possible, but it is very difficult to break this chemical bond. However, if we put the molecule on the surface, we observe this channel, because we are populating this anti-bonding chemical bond. the other way around, we don't see on the surface this fragment because we are increasing the double bond character of this system, while in the gas phase, this is a very important channel. But in addition to the just ground state reorganization of the electron density, as I told you, there are a lot of different processes. But to study the electron dynamics, it is not as simple as use the ground state statical picture. So to do this, we move to the wave packet propagation. This methodology is we are going to solve the time-dependent Schrödinger equation for a single active electron. We use the split operator scheme, so we divide the Hamiltonian, the time evolution, in kinetic plus potential energy. Since these operators do not commute, we have to split, and this introduces some numerical error, so we have to keep a small time step in order to be stable. And also it's important to say that kinetic energy is very easy to compute. It is diagonal in the reciprocal space, in the momentum space. So we apply potential energy in real space. We go to the reciprocal space using fast Fourier transform. Then we apply kinetic energy, and we come back to the real space in order to apply the other part. And in this way, we have we introduce the periodicity. Well, this is a homemade code. If you are interested, okay, send me an email or check this reference. Some technical details. It's important to say that this methodology is solved in a numerical grid, so 3D. This is the basis is a grid, and we have this imaginary potential in order to banish the wave function that arrives to the edge of the box. So if we compare this molecule, the nitroethylene, in the gas phase and in two different copper surfaces, so it is the same metal, the same chemical element, but two different surfaces, we observe that the energy and the lifetime is very different, and also the decay pattern are different. This is because on a surface, not all the waves can enter into the surface. So we have, in a metal, it is not very intuitive, but we have what is called a projective bandgap. I mean, of course, we can have electron with its energy, but not for all the crystalline momentum parallel to the surface. So for some momentum parallel to the surface, we cannot enter. So that is why we have a projective density of states, and if we have the molecular state which has no dispersion because it is a localized state, this state is going to mix with the metal continuum, but only at a given k parallel. And that is why we have this angular decay. And also, if we check the electronic structure of the copper 111 surface, we see that in this projective bandgap, we have the surface state. So the molecular state is able to couple with the surface for coupling with the metal continuum. And that is why in the case of the copper 111, the decay is totally parallel to the surface. With this methodology, we are able to study also lifetimes. And we introduce some sodium chloride layers between the molecule and the surface, and we see an exponential decrease of the width. So the lifetime, we can increase a lot the lifetime of the electron before coming back to the surface. And this is not only for this molecule. If we move to a totally different molecule, we see exactly the same behavior. So this is an universal behavior. And since I like simple systems, we can expand the Hamiltonian in the basis of the molecular and surface states, and the other terms which are not in diagonal are the couplings. These couplings are related with the overlap matrix. So if we introduce some sodium chloride layers, we are going to decouple and then to reduce the mixing between the molecule and the surface. And well, this is a picture because I love pictures. And this is very nice, how the copper, the carbon monoxide, an extra electron, if we put in the carbon monoxide, is going to relax, and mainly towards the surface. And we observe here a node, because the wave function remains, this node that has the molecular wave function is still present, because the symmetry, since we are going to mix the symmetry of the molecule with the symmetry of the surface, we are going to keep this node. in the decay. And well, now just 1 minute to some work in progress, because we can use, and we are using this methodology to study ultra-fast laser-induced processes in graphene. So we have here the graphene, and we have a lot of vacuum before the detector. So, well, we can throw electrons towards the graphene, and we see how, depending on the kinetic energy of the electrons, we have more or less transmission. And this is a way to see that we have some empty electronic states in graphene which are playing a role. So these resonances are the reason why, for some kinetic energy, this specific kinetic energy, we can minimize the transmission, have a lot of reflection. And well, and also we use laser pulses. Thank you. The typical Gaussian with the Gaussian envelope, and well, we see how the field is going to oscillate perpendicular to the graphene plane, and we are going to emit some electron density for both sides, and we can record in the detectors. So we can, using the Fourier transform, we can get the kinetic energy distribution of the photo-emitted electrons. As you can see, this is not symmetric, because this emission depends on the carrier envelope phase. And well, this is my new toy, and I am playing a lot with this graphene and laser pulses, and we are preparing the paper, and well, so well, I would like to thank Sergio Lamado Liber, my PhD supervisor, and Professor Javier Izpurua and Professor Andrei Borisov from University of Paris-Saclay for the part of the graphene. Of course, the funding, because funding is important, the computing resources, and of course, you for your kind attention.
Any questions?
Just quickly, hi. So this split step method, you said you use the basis sets like some grid or something, but you only solve for the lowest function, or are you able to solve for a spectrum of functions?
Well, so we obtain the density. So in this potential energy operator, we obtain the density from these quantum chemistry codes. So we put the potential, and this is a way, in some way, we are diagonalizing the potential.
It's just a mean field, right?
Exactly. So this is an active electron that follows. I mean, this electron is going to fill the mean field created by the other electrons. So the electron the correlation energy is, because since we are using DFT, it is included in the potential.
And perhaps just last small thing, when you said that you modeled the electron beam, so how did you impose the kinetic energy? Just by the shape of?
Well, in this case, this is the initial wave packet, because in this code, I mean, this is my code, so I can do whatever I want. And my initial wave packet was just a Gaussian wave packet with an initial kinetic energy. So I imposed this energy.
So the shape was really like wobbly. So that's how it got the kinetic energy, or?
Well, I show only. I mean, this is the shape of the laser, not the shape of the. And this is the flux of the electrons. So this is Z, this is X, this is time. So we see how these electrons are going up and down with different slopes. So different kinetic energies.
Like you said, such a wave function and let it evolve, and that's it. Yeah.
Well, the initial, in this case, initial wave function is the P state of the graphene. This is the ground state.
Okay, so let's talk about perhaps later. Yeah.
There's another question here.
Thank you, Fernando. So, what do you think would be the effect of nuclear dynamics, like including the nuclear property?
Very good question, and very computationally expensive question, probably. Well, I think it depends. I mean, I'm from Galicia, so it depends. For some things, as these forbidden transitions is going to play a very important role. because these nuclear dynamics are going to distort the symmetry, so you can induce some, well, not induce, but facilitate some transitions. But, well, it depends. I mean, if you want to put here the photoionization of graphene and you come with a very strong laser pulse, I mean, the main physics of these electrons is going to be given by the laser. And once you have ionized, you don't care.
Okay, thank you.
Thank you. Okay, so we can thank again the speaker. Thank you, Fernando.